Hi everybody, this is our lecture on section 5.1, which is on sequences. So a definition is a sequence is just an infinite list of real numbers, A0, A1, A2, A3, so on and so forth. Or, it doesn't have to start at A0. It could be like A1, A2, A3, so on and so forth like that. Or, it could start anywhere else. I mean, A7, A8, A9, A10, etc. Usually we just refer to such a sequence as AN, where the first term in the sequence A0 or A1 or whatever else is understood in some context, whether you're starting at A0, A1, or whatever else. So, for example, here's some sequences. AN equals minus 1 to the n. Right? So let's assume all of these start at A0. And then A0 is minus 1 to the 0, which is 1. Minus 1 to the 1 is minus 1. Minus 1 to the 2 is 1. Minus 1 to the 3, minus 1. And so on and so forth like that. So plus 1, minus 1, plus 1, minus 1, plus 1 for even values of n, minus 1 for odd values of n. Kind of similar to that, sine n pi over 2. Right? So sine of 0 is 0. Sine of pi over 2 is 1. Sine of 2 pi over 2, which is pi, is 0. Sine of 3 pi over 2, minus 1. Sine of 4 pi over 2, which is 2 pi, is 0. 5 pi over 2, 1. 0. Into A7. Negative 1. So on and so forth like that. So kind of similar to this one, but adding 0 terms in between. AN equal to 3n over n plus 1, right? That would be something like this. So with 0, you get 0. With 1, you get 3 halves. 2, you get 6 thirds, which is 2. With 3, you get 9 fourths. Right? With 4, you get 12 fifths, 15 sixths, 18 sevenths, and 21 eighths, and so on like that. You can also do something like this. I mean, you could have that kind of sequence and then put this along with it. Minus 1 to the n times 3n over n plus 1. It's the same as this, except now it's got this alternating positive, negative action as well. The even terms are positive, the odd terms are negative. Right? Like that. Here's an important one. an equal to n factorial. Right? What is that? Well, 0 factorial, that's 1. By definition, by convention, I guess. 1 factorial is 1. 2 factorial is 2 times 1, which is 2. 3 factorial, 3 times 2 times 1, which is 6. 4 factorial, 4 times 3 times 2 times 1, which is 4 times 6, which is 24. 5 factorial is 5 times 24. 6 times 120. 8 times 720. 50, 40. And so on and so forth. So, by the way, a general formula for n factorial is it's n times n minus 1 times n minus 2 all the way down to 3 times 2 times 1. Okay, so that's what that factorial expression is, and it, it becomes important later on. So just some examples of sequences. Here's an important type of sequence. It's called a recursively defined sequence. All right, so with a recursively defined sequence, we'll call it AN. We'll say A0 is 1. A1 is 1. And then AN is equal to AN minus 1 plus AN minus 2 for n's bigger than or equal to 2. So to make a little chart out of this, we have AN 0, 1, 2, 3, 4, 5, 6, 7. A0 is 1. A1 is 1. A2 is A1 plus A0. So that's this plus this. A3 is A2 plus A1. A3 is A2 plus A1. So that's 3. A4 is A3 plus A2, 5. A5 is A4 plus A3, 8. This one, the sum of the previous two. This one, the sum of the previous two. And so on like that. So that's a recursively defined sequence. Recursively meaning it's defined in terms of itself. All right, you have some initial conditions. A0 is 1, A1 is 1, and then after that, A2 is defined in terms of previous terms in the sequence. Okay, convergence of sequences. So with sequences, we write the limit as n, so the only limit we're interested in, sequences are only defined for integers. N is an integer. N is 0, 1, 2, 3, 4. So these are functions in terms of integers, not real numbers. Okay, so you can't do like the limit as n goes to 1, because you can't get close to 1. Or the limit as n goes to 2, because you can't get close to 2, because all you have is 1, 2, and 3, nothing in between. So the only limit we're really interested in with sequences, so we write this, or more often we write AN to mean the sequence AN converges to L. So we're taking the limit as n goes to infinity, and that's the only limit we consider with sequences. Okay, the limit as n goes to infinity. So we say the limit as n goes to infinity of AN is equal to L, or AN arrow, right arrow L, because there's no need for this necessarily, because we're never going to do the limit as n goes anywhere other than plus infinity. So we can use a simpler notation to mean the sequence AN converges to L. This means as n gets larger, AN eventually gets caught within any arbitrarily small range around L. So it looks like this. So 1, 2, 3, 4, let's make it a little finer, so on and so forth. So here's like a 1, and then you've got a 2, and maybe a 3 is over here. And somewhere there's this L, and here's the vertical line for L. And here's some small range around L. So here's L plus epsilon, L minus epsilon, where epsilon is just some really tiny number, as tiny as you would like it to be. 1/10, 1/100th, 1/1000th, 1/1000,000th. So the ANs are bouncing around, doing whatever it is that they're doing. But eventually, at some number, M, AN goes inside here. Oops, that's M, sorry. This is 1, 2, 3, 4, 5. M plus 1, M plus 2, M plus 3. This is AM plus 1, AM plus 2, AM plus 3. So eventually the sequence gets stuck inside this little range around L and doesn't leave. In other words, as n gets larger, AN gets as close to L as you would like it to be. As n grows larger, AN gets closer and closer to L, as close as you would like it to. Closer and closer to L, period. All right. So what about some convergences, some sequences that converge and some sequences that don't? So, for example, here's a standard one. 1 over n, the sequence 1 over n. What does that converge to? Well, we know that goes to 0 because we know the limit as x goes to infinity of 1 over x is equal to 0, as a function defined on all real numbers x. We've seen this before. Here's 1, and there's A1, there's A2, A3, A4, A5, A6. It's a sequence that decreases in value and eventually, gets as close to the x-axis as you would like it to be, or the n-axis, where the n-axis is where y is equal to 0. How about this one? Minus 1 to the n over n, right? This is minus 1 over n, 1 over n, minus 1 for n equal to 1 is minus 1, for n equal to 2 is positive 1/2, minus 1/3, positive 1/4, minus 1/5, positive 1/6, so on and so forth. All right, well, what does this one look like? Well, here's the function y equals 1 over x. Here's the function y equals to minus 1 over x. All right, so this sequence is bouncing up and down between the two curves. However, both curves are tending to 0. Right, so this sequence, even though it flip-flops positive, negative, is still going to 0. Right, because both of these curves get as close to the x-axis as you would like it to be. Right, arbitrarily close. Okay, this also minus 1 to the n over n factorial converges to 0. Another way to see this besides the picture above is with the squeezing technique. So let me show you what I mean about that. Suppose that an is positive in every term. So bigger than or equal to 0 for all n, and an converges to 0. Then we can show that minus 1 to the n times an converges to 0 as well. Right, just like the 1 over n and minus 1 over n, minus 1 to the n over n. Well, minus 1 to the n times the sequence an is less than or equal to an, the positive an, and it's bigger than or equal to minus an, the negative an. Right? It's either equal to positive an or it's equal to negative an for odd and even values of n. So anyway, it's stuck in this range. Therefore, right, minus, or the limit as n goes to infinity of minus an is less than or equal to the limit as n goes to infinity. Minus 1 to the n, an, is less than or equal to the limit as n goes to infinity of an. Here we can factor out the constant minus 1. Right, but we assume that this is 0, that an converges to 0. So this is 0, and that's 0, negative of 0, which is 0. So 0 is less than or equal to this limit of the flip-flopping sequence, the sequence that balances positive, negative, but its limit is stuck between 0 and 0. Therefore, it must be 0. Right? So given a sequence of positive terms that converges to 0, you can alternate the terms positive, negative, and it's still going to converge to 0. If an converges to anything else other than 0, that does not work. Okay? This is in contrast right? If an converges to L and L is not 0, then minus 1 to the n, an, does not converge. So if the sequence has a limit, and then you try to flip-flop it between positive, negative, it will not converge, right? Because what does it look like? Right? Here is the n-axis, or x-axis. Here is that L not equal to 0, and here's the negative of L. Or the other way around. It could be the other way around. It could be that L is negative and negative L is positive, whatever the case might be. The sequence an converges to L. Is that not in the middle? Right? So the even ones are going to be up around here. So like A 1000 is going to be around that limit L. A 1001 is going to be around the negative of L. A 1002, A 1003, A 1004, A 1005. Because an converges to L, the sequence eventually gets stuck near the horizontal line corresponding to L. But when I flip-flop it, positive, negative, the even terms will get stuck near the L, and the odd terms will get stuck near the negative L. So an does not converge because it doesn't approach any one number. Any one number. It approaches like two different numbers, okay, but that's not convergence. Okay, so therefore, an does not converge or diverges because it never gets close to one limit. Okay, it can't have two limits. It's got to have one limit. A sequence has one limit, and eventually it gets stuck near that limit. Actually, as close to that limit as you would like it to be, it gets stuck within that close range around the limit. So here, this one does not, because L and minus L are two different numbers. Right? So there's no close range around L that also contains negative L, no matter how tiny L is. I mean, L could be 1/1,000,000th. But then again, negative L is still, is still far away from L. So, I mean, if you take a billion, 1/1,000,000th around L, it doesn't get near negative L. Right? Those numbers can be as arbitrarily huge as you'd like them to be. Okay, so that one does not converge to L, or does not converge, period. So that's in contrast to this, all right? Where is it? Here it is. Suppose that an is positive for all n, and an converges to 0. If an converges to 0, then minus 1 to the n, an also converges to 0. And how did we show that? We used this squeezing technique. Right? Contrast this with the following. If an converges to L, where L is not 0, then minus 1 to the n, an does not converge. Okay? All right. Let's see. So, for example, 3n squared plus n plus 1 over n squared, so 2n squared plus 2n plus 2, well, that converges where? As n goes to infinity. Because these are both quadratic polynomials, right, it converges to 3/2. On the top and bottom have the same degree. Right, remember that? With limits, if the degree of the top and bottom are the same, and as n goes to infinity or as x goes to infinity, you achieve the limit that is the ratio of the leading coefficients. If the degree on the top is less than the degree on the bottom, then you go to 0. If the degree on the top is more than the degree on the bottom, then it goes to infinity. All right, so this sequence converges to 3/2, therefore minus 1 to the n times this same sequence diverges. Okay? Let's look at a sequence defined with factorials. Factorials are definitely an important, definitely something important, definitely something we want to look at here, okay? So, consider an equal to, let's say, 3 to the n over n factorial. Does an converge to a limit? Okay, well, let's take a look at it. All right. Well, certainly 3 to the n and n factorial are both positive. So an, which is the ratio of these two things, is positive as well. So 0 is less than or equal to 3 to the n over n factorial. Let's expand this expression. 3 to the n over n factorial is equal to 3 times 3 times 3 times 3, like that, over, and then the n factorial is n times n minus 1 times n minus 2 times n minus 3, all the way down to 1. So let's take this product and break it up into single fractions. 3 over n, 3 over n minus 1, 3 over n minus 2, like that, all the way down to 3 over 3 times 3 over 2 times 3 over 1. And let's add in one more factor, 3 over 4. Okay, so 3 over n minus 1, 3 over n minus 2, 3 over 4, 3 over 3, 3 over 2, 3 over 1. Okay? All right, now, these factors are all bigger than or equal to 1. These factors are all less than or equal to 1. When you take a bunch of numbers smaller than 1, their product is less than 1, right? When you multiply by something less than 1, it makes it smaller, right? So this, well, let me do it this way. Yeah. So each factor here is less than 1. When you multiply by something less than 1, it makes it smaller. So what I'm going to do now is to omit all those guys in there, and therefore this only gets bigger, this product. So this is less than or equal to, and I got to go down here. Well, let me do it this way so we can see a little more clearly, hopefully. This is less than or equal to, and I'm going to take this leading factor here, 3 over n, and then all of this, which is going to be 9/2. Right? I just got rid of all this stuff. It's less than 1. So because it's less than 1, it serves to make this product smaller. Right? So this is less than or equal to that, which is equal to 27 over 2n. Right? So 0 is less than or equal to 3 to the n over n factorial is less than or equal to 27 over 2n. So 0 is less than or equal to the limit as n goes to infinity is less than or equal to the limit as n goes to infinity, and this is just 27/2 times 1 over n. But we know that that limit is 0. So the limit as n goes to infinity, 3 to the n over n factorial is equal to 0. Okay, so these sort of sequences that are defined using factorials, they're going to play a large role in a topic that's yet to come here in Chapter 5. So that's just one example to sort of get you warmed up with it. Okay. All right. So as a final topic, let me see how long have we gone here. Okay, we're all right. As a final topic, I want to show you something about recursively defined sequences. So the bounded bounded monotone sequences. Okay, a sequence AN satisfying A1 is less than or equal to A2 is less than or equal to A3, A4, A5, like that. Or satisfying this, A1 is bigger than or equal to A2. So this is called non-decreasing, and this is called non-increasing. You can't say that this is increasing because you could have equality at any given step. So you can't really say increasing. But anyway, when you have this non-decreasing or non-increasing, a sequence like that is called a monotone. That's a nice word. A monotone sequence. And intuitively, it's clear that a monotone sequence that has an upper bound or a lower bound, one that's bounded, must converge. A monotone sequence. Well, let me see. Let's give it a name first. So a monotone sequence is bounded when there is some m such that minus m is less than or equal to an is less than or equal to m for all n. So it doesn't march off to infinity in any way. It gets stuck between some positive maximum and the negative of that maximum. It's always, stuck somehow. And then intuitively it is clear a bounded monotone sequence must converge. Here's the picture. I'm just appealing to intuition. Okay? I'm not giving you an actual formal proof. So here's this m, and here's your monotone sequence. It's not getting smaller, it's only getting bigger. Okay, but it can't keep getting too big too fast because it has this upper bound. Not that it has to converge to that upper bound, but there is some sort of least upper bound to which it does converge. So this is an upper bound, this is some least upper bound, which you may not know about ahead of time. And that least upper bound for this non-decreasing monotone sequence is what the limit must be. So an converges to L, where L is the least upper bound. So, for example, you remember that sequence Fn, right? Recall the sequence did I call it Fn? What did I call it? I called it An. Yeah. I called it An. Let's call it sequence. Fn defined as follows. It's called the Fibonacci sequence. F0 equal to 1, F1 equal to 1, and then Fn equal to Fn plus, or Fn minus 1 plus Fn minus 2. Right, so the table for it looked like this, and Fn 0, 1, 2, 3, 4, 5, 6. So this was 1, 1, 2. Some of these 2 is 3. Some of these 2 is 5. Some of these 2 is 8. Some of these 2 is 13. So on and so forth. Right? Consider the sequence Fn plus 1 over Fn. So the ratio of Fibonacci numbers. So 1 over 1, 2 over 1, 3 over 2, 5 over 3. And what is this sequence doing? 8 over 5, 13 over 8. What is this sequence doing? Is it getting bigger or is it getting smaller? Right? This is 1.5. This is 5/3, 1.6, 1.67. This is 8/5, which is 1 point. Oh, this is not an example of one that just is strictly monotone. All right. So, not strictly speaking a monotone sequence, but here we see something close to it. So recall that Fibonacci sequence. Right, F0 is 1, F1 is 1, Fn is the sum of the previous two. And here's all the way up to the 10th term, F10. Now consider the ratio, Fn plus 1 over Fn. So that's 1 over 1, starting at n equal to 1, 1 over 1, 2 over 1, 3 over 2, 5 over 3, 8 over 5, 13 over 8, and so on and so forth. The even or the odd terms, the black ones here, are decreasing. 2, 1.66, 1.625, 1.6190, 1.6181, and the red ones are increasing. 1, 1.5, 1.6, 1.615, 1.617, so on and so forth. So there's two monotone subsequences within this sequence. Okay, so these monotone sequences must converge. All right, let's find that limit. So assuming the limit as n goes to infinity, Fn plus 1 over Fn is equal to L, let's find L. All right, well, L is equal to the limit as n goes to infinity, Fn plus 1 over Fn, which is equal to the limit as n goes to infinity. Well, Fn plus 1 is the sum of the two previous terms. The two terms previous to Fn plus 1 are Fn and Fn minus 1. And then this is just Fn. So this is equal to, let's go down a line, the limit as n goes to infinity, Fn over Fn plus Fn minus 1 over Fn. All right, this is a 1. Uh, 1 plus, and then this is 1 over, okay, now I'm going to take the reciprocal of that, Fn over Fn minus 1. So that's the ratio of successive Fibonacci numbers. We assumed that the ratio of successive Fibonacci numbers goes to L, right? This is a Fibonacci, so this is a Fibonacci over the previous. So Fibonacci, this guy, over the previous Fibonacci. That's the same expression here. You're not using n plus 1 and n, you're using n and n minus 1, but it doesn't matter. They're, right, two sequential Fibonacci numbers. And since n is going to infinity, if you're off by 1, it doesn't really matter. So this limit, as n goes to infinity, this one here is L. So this is equal to 1 plus 1 over L. So now we've got this equation for L. So L is equal to 1 plus 1 over L. So L squared is equal to L plus 1. So L squared minus L minus 1 is 0. So L equals 1 plus or minus the square root of 1 plus 4 over 2. So that's 1 plus or minus. Right, so L equals 1 plus root 5 over 2. or 1 minus root 5 over 2. However, this is negative. That's a negative number, and, that sequence of Fibonacci numbers is positive, so it must be the positive limit. And this number is called the golden ratio. One plus the square root of 5 over 2. So he's a famous irrational number like pi and e, Euler's constant e. Not quite as famous as the 2, but he's got a life of his own. So that's a nice problem. Okay, that's the end of the lecture on this section.